All right, so now we are going to be looking at half-life and transmutation. So what is half-life? So in the previous lesson, we were talking about how a nucleus breaks down, and when it breaks down, it releases particles, okay? So this process actually affects the amount of the substance. So let's say if you have carbon and it's radioactive, the nucleus of carbon is breaking down, emitting radiation, and this is dropping the amount of carbon. So what we call the half-life is the rate of decay. Decay is the same as breakdown, is the same as uh, radioactivity, okay? So half-life is a rate of decay for a radioactive isotope. So we've talked about isotope in a previous unit. We said isotopes are atoms that have different number of neutrons. The atoms of the same element having different number of neutrons or different mass number. Okay, so the half-life is the time required for half of an original quantity of an element to decay. So let's say you have 50 grams of carbon, and after 10 minutes, the 50 grams breaks down and gives you 25 grams. Okay, so if it takes 10 minutes for the carbon to move from 50 grams to 25 grams, that 10 minutes is called a half-life. So the half-life is constant and independent of any physical or chemical change the atom may undergo. The half-life can be calculated at any given moment by measuring the rate of decay of a known quantity using a radiation detector. So let's check this out. A certain isotope has a half-life of 1 day. This means the amount of that isotope remaining at the end of 2 days will be half. Okay. So if they say the half-life, an isotope has a half-life of 1 day. This means the amount of an isotope remaining at the end of 2 days, it will not be half, sorry. At the end of 1 day, it will be half. By the end of the second day, that half will be half again. That's why it becomes 1/4. Okay. Now, radioactive isotopes decay at a rate characteristic of each isotope. Rates are described by half-life. The shorter the half-life of a substance, the faster it disintegrates and the more active the substance. So if you look at this curve, this is a curve that represents what? A radioactive decay. Okay, we're not going to go into those details until we be in a chemistry class. Okay, so let's look at transmutation of an element. So remember I said when you have a nucleus that breaks down, it usually changes into a different element. So the when radioactivity results into one element changing into another, we call that transmutation. Okay, so transmutation is a changing of one chemical element to another. Okay, so it can occur naturally and we'll call it natural transmutation, or it can be an artificial process and we'll call it artificial transmutation. So this is an equation that represents what? Transmutation. You can have a nitrogen atom that will absorb one neutron, and when it does that, this is going to cause the nitrogen to break down, changing into carbon and hydrogen. How amazing can that be? So natural transmutation, for example, can occur when you have a uranium atom changing into thorium and releasing helium. Okay, so when an alpha emission occurs, what happens? The mass decreases by 4 when an alpha emission occurs, and the atomic number decreases by 2. We've learned what atomic number is. When we represent an element like this number at the bottom is called the atomic number or the number of protons, while this number at the top is called the mass number. And remember, the mass number is the number of protons plus the number of neutrons. Okay, so the resulting atom belongs to an element 2 places back in the periodic table. When you look at the beta emission from the nucleus, when an atom emits a beta particle or beta radiation, there's no change in the mass of the atom, no loss in nucleons. Okay, the atomic number increases by 1. Okay, and resulting atom belongs to an element one place forward in the periodic table. Gamma emission from a nucleus does not change the mass, neither does it change the atomic number. So we have artificial transmutation. Okay, this concept kind of was introduced by Ernest Rutherford's cloud chamber experiment in 1919. Okay, so what Rutherford when in Rutherford's experiment in 1919, he succeeded in transmuting a chemical element. After bombardment of a nitrogen gas with alpha particle from a radioactive piece of ore, he found traces of oxygen and hydrogen. Since then, synthetic elements have been produced from atomic numbers 93 to 140 with short half-lives. Let's check this out. When an element ejects an alpha particle, the atomic number of the element, again, when an element ejects an alpha particle, remember always that the atomic number reduces by 2. It reduces by 2. When an element ejects a beta particle, the atomic number increases by 1. It increases by 1 when a beta particle is emitted from the nucleus of an atom. A certain element if emits one alpha particle and its product then emits two beta particles in succession. The atomic number of the resulting element is changed by. So for you to tackle this type of problem, you need to do it step by step. When an element emits an alpha particle, right, what happens to the atomic number? The atomic number is going to drop, okay, by 2. So that's -2. Now, when it emits a beta particle, the atomic number is going to increase by 1. So you had -2, you add +1 to it, and it becomes what? -1. Okay? So the atomic number of the resulting element is going to be changed by what? 0. Why? Because there are two beta particles. So you are -1 plus 1 plus 1, and that gives you 0. Okay? Radiometric dating. So this it's a form of carbon dating used for plants and animals. So we use this method kind of to estimate the years of either plants or animal remains. Okay, so let's say we look at a skeleton, we're digging the ground and we realize that there's a skeleton maybe of an animal. We can use this method to estimate how long or how old or how many years back did that element exist. Okay, so it's very important. So methods not exact due to fluctuation in Earth's carbon-14 production. Non-living things dated through uranium and lead isotope. Uranium-238 decays to lead-206. Uranium-235 decays to lead-207. Again, when you say uranium-238, that 38 stands for the mass number. An archaeological dig uncovers an ancient spear whose wooden handle contains 1/8 the radioactive carbon of a fresh piece of wood. How old is the spear? 1/8, which means that for you to estimate the age, look at the explanation here. If one half-life reduces the carbon-14 by half, then 2 reduces it by 1/4, and 3 reduces it by 1/8. So you multiply that 3 by the half-life, and you get that. So that's how old it is. All right, so the next thing is nuclear fission, but we are going to look at that in the next lesson.